Good morning. From the sublime of Don Page to the ridiculous of Jeremy Butterfield. Don was saying he wasn't sure why he was on this panel, a fortiori concerning Butterfield, but I will function as a warm-up gig for Jim Weatherall, who will talk to you about prediction in the context of general relativity. So I liaising with Jim, thought I would just show you something that you've all seen before from the great Laplace and talk about it, talking therefore about, in effect, prediction indeed in classical Newtonian physics. So here is the classic quote that everybody here will have seen. Let me report what many of you will know, that although Laplace speaks in terms of knowledge, of what the demon will know, philosophers will now tend to discuss determinism not in terms of knowledge, not in epistemic terms, not in terms of prediction, but in terms of, as a physicist would say, the existence and uniqueness of solutions to the equations of motion. So the idea will be that given the present state and knowledge of the forces at issue, there is a determination by the mathematics of the future states. And philosophers have a jargon for that, which is spread beyond philosophy, not of determination, but of supervenience, that any future state supervenes on the present state. Now, there is a folklore associated with that general notion of determinism, namely that classical physics is deterministic and quantum physics is indeterministic. It's the first thing you learned at the age of 10 or 14 in school about quantum theory. Indeed, that's probably about how you first heard of Heisenberg's uncertainty principle, that it's in the indeterminism of quantum theory. Well, this is false and egregiously misleading, and the reason it's false concerning the classical physics is that the theorem that Newtonian point particles interacting by Newtonian gravity form a deterministic system, which I admit is a theorem, but it is local in time, that theorem. Therefore, that is to say, the theorem about the existence and uniqueness of appropriate sets of ordinary differential equations is a statement that there is an epsilon in the time variable for which the solution exists and is unique given initial data. Therefore, I was reminded of this by Scott's wonderful Zeno's computer. It is, one can envisage that in a certain context, the epsilons towards the future for which you are guaranteed that a solution exists might successively diminish in size, a half, a quarter, an eighth, in such a way that after a finite time the solution fails to exist. And as many of you will know, in fact, Pain-Levé conjectured that there might be such a system of Newtonian point particles under gravity already, in fact, in 1898. And Zia, in 1992, proved that there is indeed such a system. One can arrange 5 classical point particles interacting by Newtonian gravity to explore each other's infinite 1 over r potential wells, picking up from that infinite potential well kinetic energy and transmitting it one to another by gravitational, instantaneous Newtonian standard gravitation in such a way that all 5 of them have disappeared off to spatial infinity in diverse directions in a finite amount of time, so that the solution simply fails to exist in a finite amount of time. No such phenomenon occurs in quantum mechanics, or can occur. In Simon and Reed, you will find, or similar books, you will find a proof that the unitary evolution UT can be extended for arbitrary positive and negative values of the time parameter. Okay, so there's a sense in which actually quantum mechanics without collapse is deterministic for all time in a way that classical Newtonian particles under classical gravity are not. But this is a panel about prediction, So let me just share with you two obvious points about prediction, which is the effort to determine future evolution, not so much from the given state in the world of the envisaged theory, but from observations you might in fact make. So I make the comment that quantum mechanics is here, again, better off than the classical mechanics, in the sense that, as came up again in Scott's talk, initially, states that are initially close in a classical state space can evolve to be very different later on. And we nowadays talk of chaos in that connection. But in quantum mechanics, without collapse, the unitary evolution will keep any two trajectories at a fixed distance or angle apart. My final slide then is to remark that in two respects, I admit, there is a broad similarity between the classical and the quantum as regards the topic of prediction. This is, in effect, after the academic curiosities of my 5 Zia point particles, this is my bowing to the real hard work of physical science. First of all, reality, or our description of it, is naturally arranged not necessarily in some canonical collection of layers or levels, but we usually envisage that there will be microscopic states or bottom level states subject to some law of evolution, and there will be effective, phenomenological, coarse-grained, macro, whatever word you like to use, descriptions using different variables or typically collective variables. And I'd just like to make the remark, which is important in your freshman philosophy class on free will and determinism, that there can be a microscopic bottom level deterministic evolution underpinning a higher level macroscopic indeterministic evolution. Because if one imagines in the most simple-minded way that the macroscopic or phenomenological or effective level is given by a partition of the microscopic state space, so that is to say what in stat phys you'd call a coarse graining, then of course two microscopic states that are given at an initial time as falling in a single cell can evolve over time to microscopic states that fall in different cells. In fact, that's exactly the generic situation. It is also, as pilot wave enthusiasts will immediately recognize, exactly what is happening in the pilot wave underpinning of the orthodox quantum theory with its indeterminism. And my final comment would be to say that setting aside the topic of levels, Laplace referred to an intellect which would know all forces that set nature in motion. And here, again, bowing to the hard work of what real physical science, we should be so lucky. The fact is, we don't know what the forces that are setting nature in motion in fact are. And that's not least because, in fact, the system that any system we actually study is in fact open. And of course, for 300 years, you physics types have invented impressive intellectual technologies for coping with this, everything from perturbation theory through master equations to all the rest. So thank you very much.
Thanks very much, Jeremy.